7.1, we're going to talk about exponential functions and their graphs. So in 7.1, we're going to talk about exponential functions with a base a, where x is the exponent. That's what makes it an exponential function. A is not going to be equal to 1, because if it was equal to 1, we would have a constant function, because 1 to any power would just be 1. In example 1, it says in the same coordinate plane, sketch the graph of 2 to the power of x and 4 to the power of x. So we're going to sketch our graphs by plotting points. So it gives us x values here. We'll plug in these x values. If I have 2 to the power of negative 3, what does a negative exponent do to the number? It puts it in the denominator. Perfect. So it'd be 1 over 2 cubed, which would be 1/8. Awesome. So our first point would be negative 3, 1/8. Next, we'd plug in negative 2. So 2 to the power of negative 2 would be 1 over 2 squared, which is 1/4. Then when we plug in negative 1, we get 2 to the power of negative 1, which would be 1/2. What's 2 to the power of 0? 1. Awesome. Anything to the power of 0 is 1. 2 to the power of 1 would be 2, and then 2 squared is 4. So we can plot all these points on our graph. We've got point here, negative 2, 1/4, negative 1, 1/2, then 0, 1, 1, 2, and 2, 4. So this would be our graph here. Let's do the same thing with 4 to the power of x. So we have 4 to the power of negative 3. We said our negative exponent puts it in the denominator, so it'd be 1 over 4 cubed, which would be 1 over 64. So really, really small, really close to 0. 4 to the power of negative 2 would be 1 over 4 squared, so 1 over 16. 4 to the power of negative 1 would be 1/4. What's 4 to the power of 0? 1. 4 to the power of 1 is 4, and 4 to the power of 2 is 16. So our points would go here. So they have the same shape. They're both exponentially growing. They're both increasing. But when our base is larger, our base being the 4, since 4 is larger than 2, it is increasing quicker. It's steeper than when our base is smaller. Next page, we have characteristics for our exponential functions. So just in our basic b to the power of x, if b was some number to the power of x, we don't have any transformations happening here. Just b to the power of x. Our domain would be all real numbers, so from negative infinity to positive infinity. The range would be all positive real numbers, so from 0 to infinity. If I had a shift, let's say that we have b to the power of x plus 4. This moves our graph up 4, which would also change our range. So our range here would be from 4 to infinity. So if we had a shift up or down, it changes the range. Also, if our graph had a reflection, it would change the range too. Let's say if it flipped on the x-axis and now our exponential function goes down, then our range would go from negative infinity. The y-intercept, when we just have our basic function, our y-intercept is 1. To find our y-intercept, we plug in 0 into the x. So we could just do the math there. If it changes, if we add something to it, it'll change the y-intercept, but just plug in 0 into the x and you can find it. If b is greater than 1, then our graph is going to be increasing. Just like we said in the last one, the greater the value of b, the steeper the increase. When our graph is increasing, we're going to have exponential growth. So our graph would look like that. If b is in between 0 and 1, if our base is like a fraction that's less than 1 or a decimal that's less than 1, our function is going to have exponential decay, and it's going to be decreasing. So it'll look like that. And then with our exponential functions, we have a horizontal asymptote. In our base exponential function, our horizontal asymptote is going to be y equals 0. But if we have a shift, it would change. Like if we had b to the power of x plus 4, our horizontal asymptote would be y equals 4. So this would be something like if we had 1/2 to the power of x. Or like 0.8 to the power of x, something that's in between 0 and 1. In the next example, we're going to sketch the graph of 3 to the power of negative x. So I'm going to plug in my values for x here. I'm going to make a chart just like we did in example 1. Bless you. We have 3 to the power of negative x. I'm going to plug in -2, -1, 0, 1, and 2. So when we plug in -2, we get 3 to the power of -2, which would change this to be positive. So this is 3 squared, which would be 9. If we plug in -1, we get 3 to the power of -1, which would change to positive. So 3 to the power of 1 would be 3. 3 to the power of -0 would just be 3 to the power of 0, which is 1. Awesome. 3 to the power of 1 is, 3 to the power of -1 would be what? 1/3, perfect. This would flip to 1/3. And then 3 to the power of -2 would be 1/3 squared, which would be 1/9. Perfect. All right, so let's plot our points. I'm going to go to the left to -2, up 9. The left to -1, up 3. We're going to stay at 0, go up 1. To the right 1, up 1/3. And then to the right 2, and up 1/9. So our graph will look like this. So on the last page, we said that when our base is greater than 1, we're going to have exponential growth. It's going to be increasing. How come this one's decreasing? Because of the negative x. That negative is a transformation. It is a reflection on which axis? The y-axis. Awesome. So some of the homework questions are going to ask you about transformations. If you're multiplying by a negative on the inside or negative directly to the x, that is a reflection on the y-axis. If you multiply by a negative outside, then it would be a reflection on the x-axis. If you add, I'll show you some examples. So let's say we had 3 to the power of x plus 4 minus 2. Something like this. When we add 4 on the inside, what would this do to our graph? Anybody remember? It's been a while since we've done transformations. It shifts it which way? To the left. Awesome. And then if we subtract 2 on the outside, which way would that go? Down 2. There's one on the homework that looks like this. It's something similar to it. It would be 3 to the power of negative x minus 4. How it wants you to think about it is change it to 3 to the power of negative x plus 4. So that negative is a reflection on which axis? Reflection on the y-axis, perfect. And then the plus 4 would be which way? To the left. Awesome. So even though in the beginning it looks like a -4, it pulls that negative out because that negative is being multiplied to the x and the +4, so it's actually a +4. You'll see an example like this on the homework. Next thing we're going to talk about is the natural base e. E is kind of like pi, where it's just a fixed number. It's 2.718. Keeps going. E is just a button in our calculator. For these questions, you do need a calculator. E kind of relates to what we've been doing in calculus with our limits. So the limit as x as it approaches infinity of 1 plus 1 over x to the power of x is equal to e. So we get really, really close to this 2.718 value. So this is e. We're going to use e for our compounding interest questions. You've seen this before. This is from Algebra 2, from pre-calc. You've done these questions before. You just need to know the formulas and plug in. For when we're compounding a certain amount of times per year, we use this formula, where P is our starting amount, R is going to be our rate, but it is the decimal version of the rate. So we always want to move the decimal twice to find what our decimal version of the rate is. N is the amount of times that it's compounded per year. And T is the number of years. Some common N's that we might see would be annually. Annually. So if something was compounded annually, N would be equal to 1. If something is compounded semi-annually, N would be equal to 2. What about if something's compounded quarterly? N is equal to 4. If something's compounded monthly, N is 12. What about weekly? 52. And daily? 365. Awesome. So it is also possible for something to be continuously compounding. So if something's continuously compounding, you're earning interest off of it, and it's going, whatever you're earning is going back into the account. So it's just continuously compounding on your new amount that you have. So our formula for that is A PERT. A is equal to P times E to the power of RT, where E is just the button in our calculator. P again is our starting amount, R is the rate, and T is the number of years. So if you ever see compounding continuously or continuously compounding, we're using the A PERT formula. Let's look at example 3. So example 3A, it says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it's compounded quarterly. So we'll do quarterly first. What is N if it's compounded quarterly? N would be 4. Awesome. So the formula we're going to use is A is equal to P times 1 plus R over N to the power of N times T. So what's our P? What's our starting amount? 12,000 would be our P. What's R? Awesome. We move the decimal twice, so it'd be 0.09. What is, we said N is 4, and what is T? 5. Awesome. So now we plug everything in. A is equal to 12,000 times 1 plus 0.09 over 4 to the power of 4 times 5. Be careful when you put this in the calculator. You can put it all in the calculator at once. Just be careful. That's my advice to you. Don't go crazy with it. Make sure you practice however you're going to put it in the calculator on the quiz. Practice makes perfect. I like to do the exponent first, so I'm going to change 4 times 5 to be 20, and then I'll do inside the parentheses, so 0.09 divided by 4 plus 1 would be 1.0225 to the power of 20. You can just keep every step in your calculator. You really don't have to write anything down. Just make sure you write down what you're putting in the calculator. I need to see the formula. So we're going to raise this to the power of 20. We get 1.56059. It keeps going. Keep all the decimal places for each step. Keep it in your calculator. Then we multiply this times 12,000. You should get 18,726.11. We always round to 2 decimal places because we're talking about money. So this would be our ending amount. All right, I'm confident in your ability on B and C, so we're going to skip ahead to D. But for B, what would N be if it's monthly? 12. And for C? 365. Awesome. Now, if it's compounding continuously, we use our different formula. We're going to use A per A is equal to P times E to the power of RT. So what's P? 12,000. What's E? Just E. E is a button in our calculator. What's R? 0.09. Perfect. And what's T? 5. Awesome. Now we can just plug this into our calculator. 0.09 times 5 would be 0.45. So E to the power of 0.45 should be 1.568. It keeps going. Keep all of the decimal places in your calculator. Then we just multiply that times 12,000. So we get 18,819.746. So we'll round it to 0.75. So again, it's money, 2 decimal places, and a $sign.